Right, I think we will start. My name is Hansdeep Khaira. I'm working for the Ministry of the Environment, Climate and Sustainable Development here in Luxembourg. And I will just try to moderate and facilitate the discussion here in this second workshop, where we're going to have two presentations on two specific projects. The first one will be by Hansdeep Khaira, who will present a project in Georgia. And then we will have a project presented by Bhavani Shankar about rainfall here in Luxembourg. So the way I see the discussion is that we have the first presentation, then we have a discussion about this first presentation, then we'll return to Bhavani, have a discussion about this presentation, and if we got time at the end, we can have a general discussion a bit more overarching about the issue of having and using satellite images and to support decision making. If that agrees everyone, we can proceed like that. So I will give first the floor to Hansdeep.
Right. Good afternoon, everyone. Thank you for coming. Before I begin the presentation, just a quick background on IFAD. So I work with the International Fund for Agriculture Development. It's a UN agency, and we fund projects. So basically, we lend to governments, and then we also design the projects for them and supervise them and execute the projects for them. I work with the Independent Office of Evaluation. So our office evaluates projects that are completed, closed. So it's mostly ex-post evaluation. We undertake one impact evaluation every year. So basically, it's a quasi-experimental evaluation where we have, beneficiary group and the control group. Usually, for ethical reasons, in IFAD, in any development agency, I would say, we do not randomly assign people as participants and non-participants. So basically, it's self-selection. What this means is that when we come in the end, there is no control group. There was never a control group. So we have to, at the end, come and create a control group that is similar to the treatment group. So this is one of the major tasks we have to do as part of our evaluations, impact evaluations per se. I wanted to give that context because this aspect will come up repeatedly in this presentation. So this, let me start by giving a bit context to the project. This project was in Georgia, and there's a bit of history in Georgia also because of some conflict they had in the past with Russia, which means that you may not be able to access all the regions there, and so that has to be borne in mind before you do any data collection. And because the title of this presentation also is about hard-to-reach areas, and this presentation also talks about how satellite imagery can be used to access areas which are hard to reach. Okay, this is part of Russia. Now, so this project was there were four main interventions that IFAD did in this project, and those are mentioned at the bottom of the screen. But what concerns geospatial analysis, and this presentation is the first one. So essentially, the project rehabilitated. So there were Soviet-era canals that were supposed to bring water to the farmers, but they were all in dilapidated condition because of years of neglect. And so what the project did is it repaired and rehabilitated those irrigation canals so that water could flow down to the farmers. And so the development objective was that once water flows to the farms, crop production is increased, and therefore incomes will increase, assuming there is the market. So that was the main aim of the project. So as I mentioned before, our approach my approach as an evaluator when I went there was to exactly measure what have been the economic changes in the lives of beneficiaries after the project finished. And as I mentioned, we use an ex-post quasi-experimental method for this thing. So basically, again, to give a bit of background, we had a household survey designed, and we had the survey was administered to both control and beneficiary groups. But like I said, we had to develop the control group from the start. So we decided to use geospatial analysis, not only for, or geospatial data, not only for analysis, but also for sampling. So the idea was that we would use satellite imagery to select control groups and then carry out the household survey. But we will also use satellite imagery to do it like a pilot testing on its own, a standalone pilot testing of satellite imagery, where we would look at what were the effects. I'll come to that in a moment. So, like I said, there was no random assignment of beneficiaries, and there was lack of adequate baseline data. So in terms of selecting control group using geospatial or satellite imagery, what we did is we selected control groups on the basis of these indicators that are on your screen. One, we looked at average elevation, distance to primary road, secondary road, and other indicators. Having looked at that, we compared those with beneficiary areas, and this is how we identified, let's say, villages where we knew we had to go to undertake household surveys. So we used satellite data to map these two kind of areas, yeah. And this was what was. We also used the Köppen climate classification because there can be microclimates across Georgia, and we wanted to take that into account. As you know, the control group should resemble the treatment group, and hence all this effort was made to select. So I'll just give an idea of the household survey results, although it does not directly concern geospatial analysis. So we found that irrigation communities, they did increase the amount of land. So the land they allocated to agriculture increased thanks to water, but it was a very minor increase. And this is what the household results gave us. And then we decided to check the same results using satellite imagery. So the idea was to triangulate results from the household survey, and because we wanted to see the how robust the results were. So basically we used geospatial for triangulating household survey. Household survey was still our main focus. And we looked at one particular indicator for doing this geospatial analysis, which was the change in agricultural land area. In other words, we wanted to look at, from a satellite point of view, had the area of project got more green, let's put it that way in a very layman term, had it got greener than before. And so but we wanted to look at both things. We wanted to look at what was the situation before the project and what was the situation after the project. But we also wanted to use a counterfactual and see what was the situation of the counterfactual, the control group, before the treatment and after treatment. So in a way, this was the classic difference in difference method that we use. And the difference between these two results would show what was the impact of the project. So we used what is called the normalized difference vegetation index. That is the index NDVI, which is used commonly to see the difference in the greenness cover between periods. So for the data and all this, I must mention that as an evaluator, I did not have this capacity. But we have an in-house environment and climate division, and we collaborated with them. So they had an expert sitting with me and undertaking all this. And so we used the NASA MODIS satellite image, which gives you every 8 days. And we looked at the period right from 2004 to 2016. Now, 2016 was the period when the project ended. So that was your end line, and that was important for us. But the project baseline was around 2012, 2013. But we decided to go even beyond that and looked at 2004 so that any changes, we could have designed, this way we could design a trend. Any changes happening at least before 2013-12, we would already take those into account because we had a much longer time series. So we went a little beyond that, and data was available through the satellite imagery. So we decided to take advantage of that. And all this was done freely using Google Earth. Google Earth is a very simple thing. I even have it on my mobile, so it helps you to, zero down on maps and uses the MODIS data, satellite imagery to perform analysis. Now, we used what is called the Bachi contrast. So this is the before-after control impact. And this is exactly what I had mentioned before. The before is before time period, the after is after the project, and the control is vis-a-vis the control group. So this is what called the Bachi contrast, and there was a recent research paper on that in 2016 on this index, and we used that. It was not for agriculture, but we decided to, let's say, take a chance and use it for agriculture purposes. And so what we were hoping to see was a different pattern of change, like I mentioned before, from what happened before the project and after. That was the idea. And the algorithm, we had an algorithm that was run using the R program. Our program, as we know, is free to use software, and it also has algorithms, it has programs where you can run these algorithms. I didn't run them, so I won't be able to say more about them. But yes, it's freely available, and it was easy to do, was all I can say. So what and I'll show you some images later, but just to give some more ideas. So what we decided is that we would, firstly, how do we select the so we decided to select also the non-treated sites, yeah, which were around but it was important that they are of the same land cover. They are in close proximity, because the further you go away from the treatment areas, the less the chances that agroclimatic conditions will be the same. So we wanted to stay close to the treatment areas. Of course, they were not subject to any intervention. We wanted to make sure so that there is no contamination. And then those were randomly selected, of course. So this is what we did. And in the irrigation schemes that were there, we also decided to go further and divide the plots into small, medium, and large on the basis of their size, because we wanted to see what impact does it have on different types of farmers. So the assumption was that smaller farms would be with smaller farmers and larger with larger. And our main target audience is always the smallholder. So we wanted to see the impact vis-a-vis the larger farmers. Okay, so this is what we see is these are the ones in yellow are the ones that are, these are the different schemes, let's say, that the project rehabilitated. These were the schemes, and this is actually shows the command area, so where the water was expected to reach. These we got through the coordinates which the project had. So let's see, we zero down on one, which is this one, and that border, white border shows you the command area. And so within these, we selected, fields. PRJ is a project fields, and we designated them as large or small. And then around this area, we picked up certain sites, which we call them control areas, and these again were divided into large, small, medium. So this was the way we conducted, and this is all satellite imagery data. So anyway, after we did is basically we did a cluster analysis, right? So we looked at the. This is a bit loose, so that's okay. No, this is loose, I was told. Yeah, very sensitive. Right. So what we did is in the first, as a first iteration, we looked at the pixel. Match the pixels between the treated and the non-treated sites, and we randomly selected 50 sites. We then computed the NDVI average for those pixels, and from those we selected 20 sites, and this was using the root mean squared error approach, and that's how we finally zeroed down on 20 sites that we would like to analyze further. Now, so this is what I was talking about, what is the Bachi contrast, and it's it's essentially your difference in difference. So your control area before after project minus the project area, before after, and the difference was what in the index is what gave us the NDVI and the difference. Now, interestingly, when you get a negative answer, it is actually something positive in this index because it shows that the variable has increased more. So it's increased in the treated side as opposed to the non-treated sites. So it's actually a positive thing for the project if there's a negative. If there's a positive, then apparently the project did not do as well as the non-beneficiaries did, which is a cause for concern unless there is contamination. So these were some of the results we got. On the left side, we have the leftmost column. These are the perimeter, the different scheme names. But interestingly is what we need to look at the p-values because those were the ones in the end that we used, values that were statistically significant. And in the middle column here somewhere is the Bachi contrast, which actually is the number given to the index that shows. So all the negative ones, as you see, are the ones we picked up first because they were the most positive ones, let's say in the context of the project. And then we looked at the p-values, and only those p-values which were below 0.05, we picked them up as the ones that where the project had given the result. Okay, it just needs to be. This time I didn't touch. Yeah, okay. Right, so, and the ones in the gray showed that absolutely there was no impact on those ones. So we just picked up the minus ones and then that's it. It's going to be a bit of, I need to transfer to do that. Sure. I mean, I don't know if you want to have questions in the meantime to fill time. I mean, I'm free to take those. Yeah.
Any questions so far? Yes.
I wonder in terms of resources, how much do you need them to set up this kind of evaluation?
You mean the whole evaluation or only the geospatial part? Because remember, this was a household survey, and the geospatial was in pilot. Right. So, like I said, Sure. I mean, so what you require basically is an expert's time. Otherwise, most of the data is free, right? So you can use Google Earth. I can show it to you. It's a very simple, easy to use software that we've used. And like I said, you can even have it on your on your computer. And basically, it helps you to zero down. And so these are some of the schemes that I was talking about, and this is the one we looked at. So basically, it's a free to. I usually also have it on my mobile because it's useful to actually take coordinates, and I'll come to that in a minute. We also need coordinates on the ground, without which you really cannot use geospatial analysis because you can't pinpoint the location. So this Google Earth also helps you whilst you're there on the field to take the coordinates. So it's relatively inexpensive, except for the fee that you will need to pay the expert. Well, in-source, because we have in-house, a division that actually does this kind of work, so we could use it from them. But there's another cost involved in this, and which is if you do not have coordinates, right? Then you may need to either take it. I mean, we were lucky because the project engineer had these coordinates of the different schemes. But if you don't have, then you actually need to go to the ground to get them. Or at least the areas which you feel you need to get those coordinates and feed it to the so that extra cost is involved. Yeah.
Perhaps when you just present yourself briefly who you are and where you work.
I'm Mirko Gazzini from Eurostat. Question regarding the data. So the data, as you mentioned, just the Google Earth tool, is the data you collected were all collected through the Google Earth tool? The MODIS data you mentioned?
Yeah, everything was collected. Basically, we were using pixel sizes, so all that was collected through Google Earth.
Those data usually are not radiometrically corrected
Sure.
So data very often are not accurate.
Sure.
Have you considered going instead to use a Google Earth engine where you have actually, you can collect the data, you can collect sentinel data as well, location purpose, and other form of data, Landsat data, and there the data are actually, say, accurate. Because what you have on the Google Earth, and the Google Earth
Sure.
are really, it's a few words.
Sure.
So those are,
Sure.
I mean, is there spatial errors, there are geometric errors, there are,
Sure.
it's kind of an issue if you want to have an accurate,
Sure. Well, yeah, I mean, it's good to know. Actually, that's why we went for a longer time series where we wanted to see any problems we could discover it much before rather than just focusing on that time period. So that was one of the reasons we decided to look at some trend analysis before we actually get into that. But that point is well taken about using, even better sources that are available. Remember, it was a pilot. We wanted to do it free, and so that was the...
I wonder if that's what they did, because you used the 8-day,
Yeah, we use the MODIS.
and that probably is not available.
it's not available on Google Earth. It should be the Google Earth engine, actually, where you have the collection of data.
Yeah, we use the Google Earth. Yeah.
So typically Landsat images or very low resolution.
Yeah, we use the MODIS.
This is low resolution, but,
Yeah, we use the MODIS. Let's
Let's go, it's working now, so that
Yeah, let's go before it stops again.
you come back.
So as I was saying, we found out that there was at least 4 areas in the treatment areas had a significant 0.05 p-value. But however, we found that the overall average relative contrast, Bachi was only 1.24%, which means that, in layman's term, that's been hardly 2% increase in the land area from before as it's gone? Just talking to myself. I tried and then it... Right, so basically it had just a 2% increase in the area of production as opposed to before and as compared to treatment areas. Now, in what we found importantly for us, in 3 of those 5 schemes, small plots performed better than similar plots in non-treatment, and that was for us was important. Now, there were 2 important things that came out from this particular work that we did. One was that results were quite similar to the ones that we undertook using the household survey. And this was very, very heartening for us. For example, the household survey showed when they interviewed the beneficiaries, they said there were very minor increases. They did not really increase their production because they didn't have a market. And that was also reflected in the satellite, the geospatial analysis. The other point we noticed, as I mentioned, was both household survey and the geospatial analysis showed that the effect on smallholder farmers was more than the ones on the bigger farmers, right? And so for us, these 2 conclusions gave us the confidence that the geospatial analysis work we undertook was quite meaningful, and we had confidence, and we could actually triangulate all the information that we had using the 2 sources. Now, there were some lessons learned, of course. One is, like, when you're dealing with agriculture, the problem is that when you look from top, any change in greenness, you do not know why it's happening, right? You see what is happening, but you do not know why. And that's what happens in a satellite imagery. So if the greenness increased, maybe they have switched to different crops that were let's say denser than the previous crops. So their area actually did not increase, neither did their productivity. It's just they switched the crops. But we wouldn't know that using satellite data. The second was, and therefore we feel that a field visit is essential. What you call the ground truthing. Just staying from the satellite images, you get your what question is answered, but why, to answer the why question, you really need to go to the ground level and ascertain through either household data or through other informants who can tell you what really happened. So geospatial for us is something that we cannot use in isolation. Now, preparation is the key. Like I mentioned before, having geographic coordinates is very important. In our case, we were lucky to have the delineation boundary and the coordinates, but without coordinates, you cannot really get accurate data. And finally, we feel that you can use NDVI, you can use like we showed, you can use geospatial analysis both to supplement your household impact evaluation by helping to select control areas, and then they can go and interview, or it can be the other way around where you can select a control group area through a household survey, and then you can use satellite imagery to see the difference. So, these two remain interchangeable. And this is something we were talking about. So this is, there have been a lot of developments in satellite imagery. Importantly, there's the Sentinel that has now come, and from the earlier MODIS that gives you on the top 250 meters, the distance where you really can't make out much in terms of pixels, the Sentinel actually comes up to 10 meters. So you can really see close-up pictures and understand what is happening. But the only problem there is if you're doing a long time series, you cannot use Sentinel because it starts at 2015. So, in our case, we had to go really back, so we had to use images that were not really very clear. But in the future, especially for monitoring purposes, not evaluation alone, when you're doing monitoring, every year you can then therefore use a Sentinel and see changes that are more, I guess, clear than the MODIS that we used. Thank you, that's it.
So thank you, Hansdeep. So there was already a start of a discussion during the technical break, let's say, about the fact that perhaps Google Earth images can be distorted or whatever. Are there other questions of clarification first to understand the methodology that has been used, or some comments on the methodology and the approach? Before, yes?
Why didn't you use something like crop cover or something like that, more classification done by the US Geological Survey, for example? So, because there are so many different ways. I mean, it covers a lot, and yeah, but I was just wondering, so what the rationale was, if you're really interested in crop yield or
Right. Okay. What we really wanted to do, which we couldn't, is look at the type of crop that is being produced. Right. So we had to use NDVI because in this instance we were just looking at the area expansion within that, but also if earlier there was not really anything growing. So for us, having the greenness, the contrast itself was meaningful because it would have shown us what was there and which was nothing before and what was there now. So that was the difference. Yes, the problem arises when you're looking at things like productivity, which means that the greenness cover might be the same before after, but you still are not able to figure out whether it's really increased in productivity means the area is the same and you perhaps growing more within that area. And that remains a challenge because, like I said, unless we have some heat mapping, etc., in the future where you can actually understand if there's been a change in crops also, for right now, for us, NDVI is serving the purpose, which is there was nothing and then something that grew.
Yes, there's another question from our left here in front. Yes?
Sure. I mean, we don't do that, but yes, we know of instances UN has used. I mean, there are a lot of things. One is you can see the movement of locusts, for example, because that you clearly see how that's moving. So, satellite imagery helps to early warning systems. That's why we've been using. But it also helps to, understand, for example, livestock movement, because there's a lot of cross-border movement of livestock in Africa especially, and at the time of the census, when you're taking it, those numbers can matter a lot when, the livestock has moved to the other side for grazing. So using satellite imagery, you can also control on that. But as you know now, I mean, they are also using satellite imagery to look at poverty, for example, for levels of development. So you look at how in the night time, you look at how much an area is lit before and how much it's lit now, and that is an indicator for development. That means there has been development and people have more electricity electricity. Even in the rural areas, they have more electricity. So there are several now purposes of uses being made of the satellite imagery.
Thank you. Are there any other questions from the floor so far? Perhaps I got one question, clarification question. About this greenness indicator, could it not be green also more green because there's been more rainfall? So did you take that into account, the weather actually?
Sure, yeah. Like I said, we did take, firstly we had to decide the time period, and that time period had to be fixed across all 15 years. We could not change that. Also because harvest times are, fixed and all that, so we had to look at that. And there we had some issues in cloud cover at times, and that's why we used an average of several days and not just one day. So we used it over 2 months period, and that kind of gave us an average when there were periods when there was no cloud cover. Yes, that's how we overcome that problem.
Thank you. Ah, yes. So first of all,
My question is regarding the resolution that was used. As you showed in the last slide, the resolution is 250, but when you used it, it was fairly low resolution. Was it a very big problem to use that in very small areas? Because on the control group, some of them were like sweaters, which are really small. Was there any problem with using the NDI in such a small parcel?
Well, to be honest, I didn't do it myself, like I said, but I didn't encounter any such problems being voiced by my colleague who undertook this work, because they were small, but they were not that small that we could not perhaps capture it. So we tried to keep a minimum distance where we could actually use that, and that is the reason why from 50 sites and we zeroed down into 20 sites, right? We wanted to have only those sites where we were confident we could actually use that information. The pixel size was enough for us to actually make conclusions.
no, as you want.
Right. So usually for ethics purposes, we don't share the databases, right? We have reports that talk about these. They explain the whole method, everything. But in terms of the background data, we do not share it. For ethical reasons, we are not allowed to share that with everyone. The outcomes, yes. I mean, the report has been published and it's online for everyone to see. Yeah.
Yes. Suppose so.
Just not cross-format to the use of the NDVI and not of the method, because actually to make the possibility to investigate other indicators. In fact, that the NDVI may saturate very quickly depending on vegetation that you're looking at and the density of the vegetation. So if you want actually to discriminate different type of crops and the zones which are denser than the other, with the NDVI you may not be able to do that. But just to maybe to explore other indicators.
Thank you. Any other comments for the moment? I don't see any. Oh, yes.
I was just wondering if you could mention maybe the author of the article with BACI.
Yeah, it's M. Meroni. Yeah, et al. You can Google it, and I can share with you the source after this. Yeah.
That would be great.
No
Just maybe comment it.
Sure.
I also suppose that, if you don't mind, that the presentation will be made available for...
Sure, yeah,
Yes.
of course, yeah.
For the
And there's the whole report available online on IFAD's website also, on Georgia, and yeah, but I can share the source.
Okay. Yes?
I'm also from the European Court of Auditors. I have a last question. Maybe you said you only do one impact evaluation per year. Is that because of, you don't have, you need sufficient expertise to carry out these evaluations? Because I guess you have many other projects where it could be useful.
Sure. Yeah, basically we undertake only one per year. It also has to do with budget constraints, right? Impact evaluations can be very expensive. I mean, if you do an RCT, it can be $1 million. If a quasi-experimental, it has to be a minimum of 300,000-400,000, right? So that also impacts our budget. So we usually use one where we try new innovative methods. So we did that, but also in the same project, we did machine learning. We use something called genetic matching, which is over and above the PSM, the propensity score matching, so it's even better than PSM. So we do one, but we try to use we use it mostly to promote some innovation that we are hoping to cash on. Yeah.
All right. Okay, so I don't see, for sure, any other raising hands. So I would suggest that we move to the second presentation, the one from from Bhavani, sorry. So do you want to change the computer, I suppose? Hopefully it will work better.
Good luck. Try the other one.
There's another one.
They're two different.
My only thing is the power. I hope I will have power.
Well, you have a charger.
The usual Hansdeep music. Hope it's stable. Yeah, finally. Well, there are a lot of things that we have solved wirelessly except for charging the laptops, at least these old Dell laptops wirelessly. Good afternoon. If you don't mind, I would probably stand up. I'm Bhavani Shankar, so I work as a research scientist at the Interdisciplinary Centre for Security, Reliability and Trust, SNT for short, at the University of Luxembourg. We are very close by. I'm going to talk about rainfall estimation using signaling data of a satellite communication network. I start with a couple of caveats. The first thing is, well, I'm an engineer, probably a misfit in this audience, but I'll try my best to convey what we have done. Try to keep the math and other things as less as possible. And the other thing is, today was a very beautiful day for us because we do rainfall estimation, and the more it rains, the more it's, more our networks get trained. So probably others didn't like it, but for us it was a very resourceful day. Quickly, I have to run through a list of acknowledgements. The whole project has been funded by the FNR under its scheme called Bridges, which is more like a proof of concept thing. The key researcher working with this was Dr. Ahmad Garanjic. He was with us, and he started his own company. And a list of other people here. And one of them, there is Guy. He works with RSS Hydro. He's sitting here. He's helped us a lot with this. And of course, our colleagues from SES, and then we will let you know why they were helpful. And also Dr. Andrew Ferrone from AgriMeteo, who was one of the initial supporters of the idea. Okay, so what are we doing here? Well, when we started this project, everybody started questioning, oh, why don't you predict? So what we're trying to say is that, no, we are not predicting, we are estimating. It's not forecasting what is happening in the future, but what we're going to do is to measure what's happening now. It's more or less a nowcasting. So the centrality of rain, most of us know, it impacts a lot of fields, and so it's essential that we estimate it properly. Why? Well, list of things. Well, agriculture, well, what to grow and when to grow. And of course, also for the insurance claims of the farmers. City water management, flood warning, and then insurance, finance, and real estate. So how do we, well, the claims assessment. And initially for the POC project, we had to show a commercial commercial aspect, and so insurance was chosen as one of the commercial potential of the project. Of course, transportation and weather and climate prediction. So a plethora of fields where I need to know how much it has rained. So I'll just focus on one or two of them, just quickly. The traditional thing, when it rains, it's going to flood. So the traditional flood map, which people have used for a lot of these activities, are based predominantly on rivers, tagged, but well-known sources of water and historical data. So it's used for a lot of aspects. Since it has been used, you have significant amount of data, the models are well-trained, and so there's no scope for further improvement unless there is something really disruptive. But what is happening now is these flash floods. I'm just putting this from what happened in Luxembourg in 2018. The flash floods, and it's going to be an incessant rainfall, and it could happen anywhere. These are urban flooding, and then you really don't have historical data, and you really don't have maps, etc. immediately. And what you want to know is how much it's raining now, and then you probably use some topographical data and say that, look, in 5 minutes it's going to flood somewhere else. So these things are not available yet. So what we probably would want to look at is this flash flood. This is one application that we could immediately think of. And of course, again, the rain, and then other things that we're also looking at is we don't have, well, the possibility to use, but we didn't look into further detail, is about soil erosion and then advice for agricultural practices, because we started off working with AgriMeteo, which is the Luxembourgish government agency for advice to agriculture. So we started off with that, but then we moved on a bit on the insurance, but we would be looking at this as well in the coming months. Okay, so there are many of these fields which we require how much has the rainfall, I mean, to estimate the rainfall. And why are we even looking at it? There are plenty of things that are already been there. For example, the rain gauges, but they're very accurate, except for things like today where the rain was not falling directly, but was just blown away by the wind. Limited coverage, it's basically in-point measurements, initially. There you know what has happened. And of course, a bit expensive. Weather radar, very large coverage area. They're not accurate because they send out, say for example, a beam and then it reflects back. So if you have a strong rain in front of you, it reflects a strong rain, but the rain behind that region is probably not shown well. So it's not very accurate, and of course it's expensive. Satellite-based rainfall estimation. One thing that we have issues, this is from the US and OAS. One thing we have is that these satellites don't look at the Earth. These are what we call as not geostationary. They don't look at the Earth at the same point all the time. So they keep revolving. So when they pass over your place, it's probably every 15 minutes or half an hour, depending on how many satellites you put in, that you're going to look at a particular place in every pass. So the satellites keep rotating faster than the Earth. So if you don't really get a temporal resolution, you get once in every 15 minutes, once in half an hour, etc. There's a new thing that is happening nowadays is opportunistic use of commercial links. So for example, you have the microwave links. The microwave links operate in a very high frequency, which are very sensitive to rainfall attenuation. The signals get attenuated by rainfall. So they're trying to, and then these microwave links are plenty, so they're trying to use this information for computing the rainfall estimation. Of course, it's not very much commercially deployed, even though a bit of Ericsson is now trying to come up with base stations which allow you to tap into this information. But then, of course, there are different mobile players. Each of them have their own base station, so I need to talk to each of them to get some data. And then, usually they are in, well, you see a lot of cell towers in the cities and the urban area where anyway you would get the data, but if you look at semi-urban or rural, probably you fail. So in general, so the accuracy would be as what's mentioned here. So what is that we are trying to do? We are trying to not use the satellites which are for weather prediction or weather monitoring, but for the commercial satellites which are used for communication, and we use these communication signals in an opportunistic way. So what we say is this. Look, the satellite signals, the ones that are coming up now, they're in a band which are severely affected by the rainfall. So if you see any variations in the signal, you could measure, or you could relate it to rain and the clouds, and then you could kind of, with some algorithms from signal processing, machine learning, anything, so you could try to get an estimate of the rainfall. What are the, so you would have, so how do I even get to know any of these things? Is that you have all these dishes on the, well, not the TV dishes, but mostly the VSAT dishes, which are kind of available mostly in the rural areas, or they're much more than all the rain gauges and other things. So these terminals, they usually report the signal strength, the strength that they measure, to a central gateway. Every 5 minutes, you tap into the gateway, you have access to all the signal strength measurements of all the VSATs in the network. So you really don't have to go to each of them and query and get. So if your operator allows you to query the gateway, then you have information about all the terminals. And usually, unless otherwise specified, the operator also has the location of the terminal. So you have the location of the terminals, and you have the variation of the data of the signal strength every 5 minutes. So you tap it, and then you have the data. Now it's up to you to, now it's a matter of how to extract rain information from this. I mean, is this all science fiction? Or are we trying to say something interesting? This is what we do. For example, this is from the weather station that's installed at SES premises in Betzdorf. It's a rainfall thing. So you would see the rain intensity millimeters per hour in the first plot, and then this is the collocated user terminal, and then this is the signal strength. Now, if you see that whenever you see rainfall, significant amount of rainfall, there is a significant drop in the signal strength. So there is a significant correlation between the two. And so this kind of tells us that it is, the idea is fine, at least it's not outlandish, but you could have to still a bit work more to get on the ideas. For example, then the things that we have to look for are these small variations. The signal strength is not fixed exactly at one level because the satellite, even though it's stationary, it keeps moving up and down, and then when it's hot, when it's morning, then the satellite components get heated up, and so you get a different signal, and it's cold, it gets a different signal. So things change a bit here and there. And also the amount of drop depends, and then this level that we mentioned here is for a particular terminal and for a particular satellite. Some other satellite and some other terminal with a bigger dish, you will have a different level. So you have data, what you are interested is in the drops, not in the actual values. And so you have to do some further understanding of where and how to do these things. So then rains and clouds, while we are still, rain and cloud has different impacts. The cloud attenuates a bit, and then the rainfall, you see, it attenuates significantly. So to some extent, you could also differentiate between the cloud and the rain. What we are trying to see is also if you could do something with the hail. Hail is a very difficult quantity to see how the signal strength is affected. For us, we don't have ground truth, so we really cannot know what to do, but then that's an interesting research problem for us. So what do we offer? What does this opportunistic use of satellite communication gives us with respect to the state of the art? The thing is that you have VSATs which are much more than rain gauges. So and then you have a much larger coverage. And then it's not that you're going to install a VSAT. The VSATs are installed by commercial entities which are already in use. So really there's not much of cost for you to go and put a VSAT. Then, of course, it's densely sampled in space. So you have a very fine sampling of the space. And then so you kind of measure what is happening at that point, not like a weather radar which has this path average measurement. So this convective efforts, as we call it. Satellite-based rainfall estimates, the idea is again the same thing. So you don't get a very good temporal resolution. So the satellite passes your place every 15, 20 minutes, depending on how many satellites are there in the orbit. And then, of course, it's low cost. And with regards to terrestrial microwave, which is the very close counterpart of what we are trying to do, is that unlike the mobile communication scenario where you have the terrestrial microwave, there are very few operators of satellite communication systems. And so if you can get access to their gateways, then you would have much simpler ease of getting data. So there are some advantages for us. Okay, so that was the idea. So where do we get the data from? So far, what we have is SES, the operator from Luxembourg. So they've given us access to data from about 35, recently a bit more, in the IFAD region of Germany for this pilot study. And so this data from each of these terminals, the data for us is the signal strength that is measured, is available at a central gateway in Betzdorf every 5 minutes. And then we have a single web interface to acquire all the data of all the terminals. And of course, we need to do some training. We need to understand a lot to get the ground truth. What we used is the data from DWD. And from the German weather agency, we get the weather data and the rain gauge data. And what we're also trying to do with the project is to set up our own weather station and a rainfall and a terminal on top of our building. That's the one on the right. And on the left, you have this, the Eifel region in Germany with the terminals. And then it's about a 25 square kilometer area with about 35. Now I think it's a bit more terminals that are available to us. So this is our data. And what do we do with the implementation? So what do we have is you have a time series. You have a series of signal strength measurements, and I need to estimate some parameters from that time series. So you need the time series of the satellite measurements, and you need the time series of the rainfall estimate. So I need to correlate one on the work. So I need to get one from the other. So you could directly work on the signal strengths. You could use any of the algorithms that probably we didn't try, but the researchers elsewhere have tried. But what we have done is to do is this. So we split the time series into dry and wet regions. So we classify the things. So then the reason is that, as I mentioned, what we are interested is not in the exact SNR values, but more the signal to noise ratio or the signal strength values, but it's the drop. And this drop could, so we need to know a baseline. So from where should I take the drop? So that would give us the dry region. That is why we need the dry regions to give the baseline. And then the wet regions provide the drop. And then you get the signal drop, and then there are traditional ITU models to get from this drop, how do I get the rainfall estimates. Of course, everything has to be taken with a pinch of salt. There are, as we started, we realized that there are many forms of rainfall, and each of the rainfall forms have their own models. But to a large extent, we are looking at very high rainfall, so more or less the model that we chose works. Yeah, so I would probably not go into the details here. What we try to do is to essentially find out good features that let us devise when it's raining and when it's not raining. So the problem I mentioned is that there are signal strength variations even otherwise in the dry regions because the satellite is a bit moving here and there, or it's because of the temperature effects, or the operator feels that it's a nice sunny day, so they just pumps up the power on the satellite. So there are some things that are beyond our control, so we have to automatically our algorithm should take care of it. So we devised a couple of feature vectors, and based on those feature vectors, we tried to use to classify based on three things: dry, light rain, and moderate and heavy rain. The reason why I put light rain is that it has a different model, but what we are mostly focusing on is dry and heavy rain. I'm sorry for the typo, it should be 3. And then the ground truth is the co-located rain gauge in Betzdorf, and the nearest rain gauge that we choose we found out in Germany. So 1 or 2 of these are considered for ground truths. We also used a bit of radar, but we were not very sure how accurate the radar is. So the closer you are to the radar, the better is the accuracy. So we try to focus a bit more on the rain gauges itself. The panacea for all problems is not to think, but let the machine do our stuff. So we did a couple of things. I am also not very comfortable with this slide. We did neural networks to classify. But one thing that we should understand is that when we feed any artificial intelligence or thing, you expect the data has reflective of all the possible classes in a kind of more equal way. But in our case, you usually have a long spell of dry, and then you have some rain, and that rain is for a short duration, and then you again start having a lot of dry regions. So traditional neural networks will not be able to capture this correlation. So there are a few other sophisticated methods that was used. So essentially, all these were used to classify the region into dry or wet. And then once you have it, then you try to do a curve fitting based on the ITU or models, so you would get the rainfall estimate. So RS is the rainfall rate, R is the rainfall rate, and you use a standard formula to get the rainfall rate. So from the SNR measurements, we classify it into dry and wet. From the dry and wet regions, we find the signal strength drop, and from the signal strength drop, we use the traditional formulas to get the rainfall rate. This is our flow. I would skip this, it's a bit more detail, but I would just try to show you one curve just to show the proof of the pudding is in the eating. So here is the accumulated rain from the weather radar is the black one, the blue is the rain gauge, and red is what we have estimated from our algorithm. You see the discrepancy, it's collocated, the rain gauge is collocated with the terminal, so, and we assume that the rain gauge is the, well, in the absence of anything, so we assume that the rain gauge gives us the perfect estimate. So we are close to the rain gauge, and we are following it, unlike the weather radar, which is a bit off, because what we are measuring is at Betzdorf in Luxembourg, and the nearest weather radar, German weather radar, is probably is in the Eifel region, about 100 kilometers, 150 kilometers from Betzdorf. So the farther you get, the less is the accuracy. So I'm just quickly finish a few things. So this project information, Rafael, which we called, it started in July, ended in 20 Jan recently. And then what we proposed were two things. One is the digital rain gauge. That is what we try to say. You have the terminals, and each terminal can be seen as a rain gauge. So each terminal is sampling the rain field. And then we did, from each of the terminals, you get what is available, and then you try to create a rainfall map in the region. So this is what you could use it for, the flood risk and other things. And then, yes, so there is a spin-off from a former colleague of mine. Yeah, so this, again, is the product. What I would like to show is one particular thing for which I thank my colleague here, Dr. Schumann. So the idea is, well, you had the rainfall, so what is it used for? So here is the flash flood with topographical information. So Dr. Guy Schumann provided us with the topographical information. So what we did is, we took the rainfall estimates and we superimposed on a topographical information to see where and how the floods could happen. I should... Okay, so now you could see, this is rainfall data from our algorithm, and then it's just to show that where floods could happen in more or less real time. I would say 5 minutes is our delay. Yeah, so this is... unfortunately, we also have a tool, but I could not demonstrate it here, so it requires huge bandwidth, and then there's some developments. So as and when the tool is available, maybe in the updated presentation, I will put it up with the links, and then you will have a... and this is the dissemination that is there. Everything is public, all in the things. Yeah, so that's it from my side. If you have any questions, please, I'll try my best to answer. I am not a hydrologist or anything, so.
Thank you. So thank you, Bhavani, for this detailed presentation with maps at the end and also some formulas and networks. So I'll give the floor to the audience to see if there is any questions on this presentation. I see several hands. Let's start on the left here.
I'm Oline from the EA. We just wanted to know whether there are other confounders than rainfall that could affect the strength of the signal. You showed us clouds or maybe hail, but are there something else than rainfall that you could confound with?
It actually depends. There are a lot of things that impact the rainfall, the signal strength, but it depends on in what frequency that we are operating. For example, if I were to use a laser, even a very small thing could impact it. But in the frequencies that we are operating, we would think that it's only rainfall and the clouds.
All right.
And hail affects, but we don't know how it affects, because we don't have a ground truth there. In fact, that's the region where in the equatorial regions where it rains very heavily, so they use a very particular band for satellites. The C band is the old C band, because that is very robust to rainfall. But in the frequencies that we use, it's very sensitive. So it's rainfall and clouds.
Okay, yes?
Sorry, this will be very technical, but I worked in the similar field in hydrolocalization using signal attenuation
how do you gather the location information? Because essentially it's a topographic problem, so your signal is disturbed somewhere, but you're not sure where. So you always assume it's at the end of the line because rains happen very close to the surface?
No, this is a very good question. In fact, what it is, it's not, the rain is a path average, because I have a terminal here, and the signal passes through 5 kilometers of atmosphere, or depending on the elevation. The satellite is there, and I'm looking at that direct, depending on the elevation. So the signal passes through a certain amount of atmosphere. So what you have is a path average. It collects all the information. But what we only claim is that this is not, the atmosphere that really hits the signal is about 5 kilometers. And so you really don't go beyond 12.5 degrees in elevation. So you really don't go very far in the atmosphere compared to something like a microwave links which run tens or hundreds of kilometers. So that's, in fact, yes, it's a path averaged measurement.
Second question would be if you have considered like crowdsourcing in this project, because of course any GPS receiver will also collect RSSI information of each satellite. So is that an interesting frequency, or is it just that this frequency would not help you in your research?
The GPS, I think, not much. I mean, if it's a cloudy day, if you go on the GPS, it still has a problem, but then once you're logged, it is fine. But we need to go higher in the band.
Actually, I think it's I'm Lee Schumann, I'm actually the RSS hyper, so the one that provided the model to put there. And actually there, just bear in mind, everything flooded because we used their localized storm event everywhere. So this was the wrong assumption model, so therefore it's flooding everywhere. But anyway, coming back to your question about crowdsourcing is interesting. I'm not using GPS, but we're working with myself at RSS Hyper, I'm working with the Talkwalker, which is a Luxembourg SnT company looking at Twitter and all social media across the internet for commercial advertising. So I'm trying to see if I can use the API to investigate what people say about rainfall, when it rains and how much it rains. So it's not, we use the GPS for the location in that instance, but not for the assessment of rainfall intensity. But we're using crowdsourcing to see from a social networking point of view how many people tweet about, oh, it rained a lot, or it didn't rain. So this could be a cross-validation of their method as well. Because what we noticed is we tested the 2018 flash floods on Twitter and all on social media. What we saw is actually a very nice temporal correlation with people tweeting not when the floods start, but when the rain starts. So people don't talk about necessarily flooding, because I think when it's flooding, people have other stuff to do. But when it rains, they do think about the rain. So flooding is usually a lag in time, so when it floods, it has already rained a lot. Also locally, so people tweet with the rain rather than the flood. So this could be a very good cross-correlation with their rainfall valuation. So it's not the crowdsourcing you were asking, but it's some form of.
Okay, so I think there was a question from the Court of Auditors there. Yes.
Yeah, I have two questions, but now that you were talking about it, the first one was about the algorithm. I wonder if this model is only specific to the IFAD region in Luxembourg, or is it different?
Yes, the algorithm itself is can be used anywhere, just that the algorithm has some parameters that need to be tuned, and that needs to be probably tuned for the region of interest. Depending on how much information that I have and how much ground truth I have, I would, because in this algorithm there are some still, I said K and alpha, so there are some parameters that you need to tune, but the general functional form is the same. It's valid for the. What is more critical is the what kind of rainfall does it reflect? It reflects very heavy rainfall. I think I shouldn't be talking the convective and stratiform, different kinds of rainfall. Maybe Geek, you can help me here. It's valid for certain kinds of rainfall, but the regions, I think it's across the regions.
And the other question was, how do you collect this data from Twitter?
So the IFAD has a lot of these projects now where you can group with universities and commercial entities. So I'm kind of in between, academic plus commercial. But you can easily take something like another company on board and have some funding inside the project to do this. But in long term, it's a good question how you would. I think you would have to show them an interesting business model. Where you would say for hydrology, it makes sense to continue monitoring this, and it's not expensive, but of course for them it needs to be attractive. So I don't know, we can't be talking about these kind of things. How attractive is something like using Twitter for environmental research? Because they will say that most of their revenue I think comes from seeing how things are advertised on Twitter. It's like how people like certain products. So it's very different to hydrology. Hydrology is much less appealing.
On this context for us as well, the data that we get is nothing what the user is saying, but just some signal strength measurements. So but then the problem sometimes is the location. If I don't know the location of the user terminal, which typically is anonymized, or you get in a region of 5 by 5 kilometers, then it's a problem for us. So we have to kind of negotiate and discuss and things. For us in this project, at least we were lucky because SES was managing and these were more community services. So all these were kind of well known. But then there's always a problem of where is the terminal.
So yes, I see questions there. One of the two. So this time you start first.
So, and then also there's some Italian. So, and then with the flooding and rainfall, there's very different terminology that people can use. So it's not because in German you can say you can have many different words for describing this is a high rainfall event. So this is the main challenge in Luxembourg when you look at it. Very different for the US, I would say, where you could be sure yes, many more people have geolocation on, many more people tweet in English, maybe Spanish, but that depends on where you are. So yeah, for Houston we saw a lot more correlation and much stronger than before. But of course Houston flooded, Texas flooded the size of, 2 times Belgium in terms of flooded area. So that stayed for weeks or up to a month. So people got active. In terms of flash flooding,
Yeah, please.
So the hail, this would be really interesting also from an insurance perspective, I would say, because hail is a very damaging type of rainfall, and a lot of things that get damaged are insured, especially in Luxembourg, so like cars or roofs or something like this. So it would be very nice if you found a way. I was wondering maybe if you bring the temperature.
Yeah, we need additional information. This probably will not give us. And also, as I mentioned, we didn't even have a ground truth thing to
Yes.
get the thing. So now we have our terminal. Maybe we can now annotate this is the region of A, this is not the region of A. So then we try to do that.
Okay, there's also a question from the back of the room.
Experiments being carried out by the European car producers to actually use the information from the car screen wipers,
Yes.
which activate with rain and which obviously go faster when the rain is more intensive. So you can also get quite accurate observation of where it's raining at any given moment, provided there is a sufficient amount of cars in that place.
We looked at it because I think there was some Volkswagen was quite public time ago. But again, unlike the mobile communication, the automotive segment is also fragmented. So I need to find out from Volkswagen, from BMW, from everybody to collect data. There's no one place to collect data.
I know they're not very keen to actually give the data away.
So this we read. In fact, one application was that in the car, this is going to be used for the renewable energy sources. So for example, when the car is going and then it says that fine, it's going to rain or something, then the renewable energy thing switches off its renewable energy way of collecting, producing the energy and switches on the more coal-based or thermal or whatever based thing. So they would, this was a plan for the German electricity grid. There was some article for, to predict this so that the grid is not in outage. So that they get into enough power because before the clouds hit and then the solar power generation goes down. So there are some things like that as well.
The second question, so as, let's say, as the society and economy is moving into towards more data intensive, I would say the path is clear, and then we're moving to the Internet of Things, so basically we're not only ourselves, we are connected and we have devices which are connected and which send signals which can be detected, but also individual objects will be connected one to each other to the network. Do you see this as a great opportunity for such predictions, for observations, because the more signals travel and the more, I guess, things can be detected from them, so ultimately perhaps you won't even need meteorological institutes in the future. What do you think about that?
No, I would say that yes, they would help, but would not probably replace any of these things. So they would be complementary or adding a few more bells and whistles to what is being done by the meteorological workshops. So we actually, the general principle is that, well, we have this machine learning, all these kind of things coming in, but then there is only so much that they will do, but then you still need the old stuff to go on. For example, for all these things, we don't even know whether those signals reliably collect the information that, or the impact of the phenomena that we want to measure is reliably seen in the signals variations or in any of the variations, or how could the signals be spoofed? There are a lot of these things that come into picture. So I would say all these things should be replaced. Of course, they will be complemented with probably a better solution.
All right. Any other questions? At least on Bhavani's presentation. Yes.
How fast? So you say one of the problems is this baseline. You have to situate that baseline from where you calculate the drop. How fast with the processing can this be done? Because I think this changes quite a bit from region to region or rainfall to rainfall.
No, I think once the network is trained, you just give it the data and then it keeps throwing out. It then depends on how fast the processors are. But to train, it takes a significant amount of time, but once it's trained, it just...
Okay, so once it's trained, it's good enough.
It's good enough. So usually what we have is a lag of 5 minutes because that's the latency in the transmission.
Yes?
Just a comment on the comment.
Yes?
Provocative comment from my colleague, whether the meteorological centers will disappear or not. I think they won't. And I think in general, the workshop is about big data, the use of big data. I mean, we may nowadays use traditional data, but we still need the domain specialists. Those people who are those who transform the data that we have, new data, which are not traditional ones, into business needs. So you have all teams of people who know about meteorology that connect the meteorology question, issues into what they come to Internet of Things. So you will still need those specialists, and I think it's essential to see that it's not yet to replace, but to complement. And I think, I mean, when we say it, don't want people to be afraid, we have to say that we're going to complement the traditional data and not replace what we do.
Yes. But also what I see, I think, is a certain shift in currently, or maybe a bit more so in the past. If you control a certain data set, basically, you were the only one who could actually process and analyze the data, and you could derive some insights from it. And for instance, base your whole business model on the fact that you had control over a certain data set. Now you will see the data can be derived from so many different sources. So all these also commercial companies, but also institutes like statistical institutes or meteorological institutes who have to rethink their positioning and their, let's say, role in society, because they can no longer base, let's say, their importance on the fact that they control a certain data set. But they will still be needed in order to actually derive some meaningful insight. That's a different story.
Okay. Any other questions to Bhavani? So we still have half an hour. So perhaps following the latest intervention, do you have more general comments on the use of this kind of information, not to replace, as you say, but to complement traditional? And you also said that Bhavani, that it needs to complement some. And also in ANSI presentation, they need to complement what they learn from the satellite images with some field survey and matching. So is there any general comments about these approaches that you want to share with the audience? Or? I don't know, but just because we got half an hour, otherwise we can also go for a longer coffee break.
No, I think what was just said, sorry, I got everybody in, but I totally agree. I think we are now entering an era where people have to be careful when they think about data protection. And I want to have it for my own business, like also IP in general. Right? So these organizations like openpatent.org, they try to advocate exactly for something like this concept where you have a patent as
some future applications in the field of, we were talking about insurance, obviously, but I mean, there are, I mean, here in Europe, most of the work in Europe, you could so apply this for commercial purpose to better estimate insurance losses, for example. But first, you mentioned also that this method could be replicated in other regions of the world. So maybe some less well-off regions. I'm thinking, for example, about India, where there it's more about microinsurance, and researchers and microfinance centers spend quite some time again with surveys in the field, working in microinsurance, trying to estimate not only the flood itself, but also damages. And aren't there two different ways of applying this information, or what you have here, like more in a developing country setting where it's more commercial purpose, or then in developing countries like India, for instance, in the microinsurance country?
I mean, so one thing probably is that in that region you have a lot of on-ground data through the thing, so it's probably much more efficient to do that than use any of these techniques, which are kind of more derived data. But otherwise, yes, I mean, as I've always said, that they always complement each other, so they don't replace one another. Yeah, I mean, insurance and these were just things that we started to look at, but then for us it was a proof of concept, so we had to mention a few things about the commercial aspects. But we as researchers were more focused on trying to figure out how things go with the opportunistic use of satellite communications.
Yes, please.
We also don't have much in Luxembourg, actually. So, no, I mean, I think we'll probably try to differentiate between the two aspects. One is a more research-oriented aspect where what can we do with this? The other one is a more commercial aspect. So what we focused on was regions where we already have these receivers in place, and how do I use it? And that was but if I want to install the receiver and then act on it, well, if it's a small, if couple of receivers, for example, what we were thinking of also in Luxembourg, probably put a few tens or 100 receivers probably in the communes and see how things work. Yes, this is manageable, but then going beyond that, I think then the idea is probably not commercially viable.
Okay, I think I don't see any other questions from the room. So thank you to Hansdeep and thank you to Bhavani for the presentation. Thank you also for the audience for the questions and the interest. So there's I don't know if there's coffee already served, but I think we start again at 4:05 in the plenary for the conclusions of the 3 workshops. So we'll see you in about 30 minutes.